Alright, so today's pre-lecture video, what I'm going to do is talk a little bit about the pointing vector, which is going to be towards the end of the chapter, and so I was worried that we might not get to it, or we might rush through it at the end of class tomorrow. So that is what we're going to do. So we learn in this chapter about electromagnetic waves, which consist of varying electric fields and magnetic fields that are created by an accelerating charge. And the way that it works is that the electric field is oriented one way, so in this picture it's oriented along the y-axis, but it also is changing, so it's going through its sinusoidal motion as time goes on and space. And then the magnetic field is perpendicular to it. And then finally, the direction of propagation, which in this picture is also shown as the direction of the pointing vector, is perpendicular to that. And the direction of propagation, we learn, is given by E cross B, which is also going to be the direction of the pointing vector. So in any case, when we talk about these electromagnetic waves, one of the things that we talk about is as they're moving through space, and interestingly enough, these electromagnetic waves can move through a vacuum. They don't even need a medium to travel through. They're carrying energy with them. And so that's one of the ways that we can think of them as transporting energy from one area to another as they travel through space. And so what we use is this vector called the pointing vector is used to talk about that transfer of energy. And the pointing vector has the units of power per unit area. So we're going to look at that because I think it's actually really helpful to think of the units when we're thinking of the pointing vector and trying to understand what it does or what it is. Remember, power is energy per unit time, and then we have times area. This is a lot like a flux that we learned about when we talked about fluids. I think was the first time that we saw a flux, where we're talking about the flow of something per unit time, per unit area. And so in this situation, we're talking about energy. And again, I want to stress that I think it's helpful to remember these units when we're looking at the problem, and we'll get to that at the end of this video. So in any case, the pointing vector, which talks about the flux of the energy as the wave travels through space, is given by E cross B divided by mu naught, and that is how we calculate it. Notice that the direction of the pointing vector is the same direction as the propagation of the vector, which of course makes sense, it should. So the thing is that when we look at our electric fields and our magnetic fields, because they're traveling waves, they're constantly changing. And so, this is what the electric field looks like. It's just a traveling sinusoidal wave. The magnetic field looks very similar. And so when we're talking about the pointing vector being 1 over mu naught E cross B, you can see that, it's going to be a constantly changing value. And so what we like to do is think of, what's the average value? So the average value can be found by taking the integral of EB, because they're going to be perpendicular to each other, over time. And we would do it over one period of the motion. But we're not going to go into that much detail, but I just want you to look at this, because if we do substitute these values in here, right here, we'd get the maximum, or the amplitude of the electric field and magnetic field times the cosine squared of kx minus omega t dt. And then we'd say, what's the average value of cosine squared? Well, the average value of cosine squared is going to be 1/2, because cosine normally goes from -1 to 1, but if we square it, it's just going to go between 0 and 1. And so what this means is that our average value of the pointing vector is going to be the maximum amplitudes over 2 mu naught. Now, earlier we learned that E over B is equal to C. This ratio is true when we're talking about electromagnetic waves, and so we can use this, and also the fact that c, which is the speed of light, can be written as 1 over the square root of mu naught epsilon naught. We can use this to write the average pointing vector in a couple different ways, and we're just going to look at those. Like, for instance, we could substitute b with e over c, and so we would get em squared over 2 mu naught c, or we could also write it as 1/2 the square root of epsilon naught mu naught en squared. And we could do other things with the maximum magnetic field as well. It's just a matter of, what values are going to be convenient for us. And so this is where we would talk. Now, the average pointing vector we often call the intensity. How intense is that energy that's coming in. And again, all we see are these different ways that we can express it. And what I want to do now is I want to use these pieces of information and look at an example problem. So in our example problem, we're talking about a 75-watt incandescent light bulb. So remember, that's a power. And we can model it, or imagine that it's a sphere with a diameter of 6 centimeters. And if only 5% of the energy goes into visible light, the rest is non-visible infrared. So basically they're saying that only 5% of this power is going to be visible light. So the intensity at the surface, now what we can think about, what does the intensity mean? The intensity is the power per unit area, and then this would be equal to, now the power, you might think we use 75 watts, but only 5% is going to be visible light, so we'll take 0.05 times that. And then the area, the surface area of the bulb, is going to be 4 pi r squared, so the radius is going to be 0.03 squared, and that would give us our intensity. And once we know that intensity, whatever this number is, we could also find out what are the amplitudes of the electric fields and the magnetic fields for this intensity. So we could use any number of the expressions that we just derived for the intensity. We could use this one to help us figure out what the E maximum is. And then we could also use the fact that Bm is going to be equal to the maximum electric field divided by C. And so that's just an example of the type of problem that we might run into.